All right, so we're going to go through section 5.1, the power series. So this is a big review from Calc 2. So a lot of this will be familiar to you. Should ring some bells. So what is the power series? So it is a way, well, it's given by this. That should be an n, as n equals 0, up to infinity of a sub n x minus x naught raised to the n power. Let me write that not a little bit better. And let's clean this up too. Much better n and 0. Okay. And if you would go in to the summation, you need a naught, a1, x minus x naught, plus an a2, x minus x naught squared. And then it goes on forever. So when we talk about this summation or the series, however you want to think of it, we will know whether it converges and then whether it converges absolutely. Now, whenever we say converges, we're going to do the limit as m goes to infinity of the summation, but it's going to go n equals 0 up to m a sub n x minus x naught the n power. And let's make that a little cleaner. So we take any partial summation, we take a finite sum of this, and we see if we can get a pattern developed. And then we want to take the limit as our m then would go to infinity. Now, whenever we talk about that converging absolutely, we want the absolute value to converge. And we could split this up a bit. We could do an absolute value of that part, and then an absolute value of the other part. So, and if something would converge absolutely, we know it's going to converge normally. Because if we have all opposite values, that's all positive things we're adding together. When we take away the absolute values, there might be some negatives. So we could possibly get a smaller sum when we're done. But be careful that whenever something converges normally, it might converge absolutely, it might not. We don't know. So we can't say anything. So converging absolutely means it converges, but converging doesn't say anything about converging absolutely. Next thing we want to look at, our idea of our radius of convergence. So it's going to be a p-value that makes our, so it's some p that's greater than 0, such that, I can write that out here, such that we converge power series converges for the absolute value of x minus x naught being less than p. But it will diverge for this being greater than P. And now, whenever we get the fact that our X equals X naught, that's called being analytic. So our summations in our power series are always going to converge when X equals X naught, because everything's going to be 0. So that situation, we call that analytic. So, and when this happens, that means that our P, or actually it's our rho value, it's not really a P. I'm sorry, I'm getting massive text. There we go. So actually it's a rho value. So whenever the rho equals 0, that's when it will converge only at X naught. So if the only place it converges is where it's analytic, then we say that our rho, our radius of convergence, is going to be 0. If our radius of convergence is infinity, then it will converge X values. So what we're going to do is look at all that summation, and we want to see, do certain values make it work, do certain values not make it work. So we're going pretty much a distance away from our X naught to see what works and what doesn't in terms of convergence. So just looking at a quick example here. Let's find, of course, the book does not. Okay, here we go. In order to do this, we are going to use our ratio test, root test, our different convergence tests that we that you talked about in Calc 2. So let's do a quick review of that. Then we'll do some examples later on. So first one was the comparison test. So in order to do this, you had to know when something converged, or you had to know a series that diverged. So in this case, let's let the absolute value a sub n be less than the absolute value of b sub n for all n values. So we have two different series. Summation from n equals 0 to infinity of a sub n, and summation of n equals 0 to infinity of b sub n. And now if we know something about one of them, we might be able to tell something about the other one. So if the series with b sub n, and I'm not going to put the indices from 0 to infinity just to save some writing there, converges, then our a sub n also must converge, if I can write it legibly. Because if the big thing is going to sum up to a finite number, then if you're adding up smaller stuff, it's also going to add to a finite number. But now, if our summation for a sub n diverges, then the summation for b sub n will also diverge. So it's a bit of a follow the leader. If the big thing converges, the little thing converges. If the small thing diverges, then if you add up more things, it's going to be even bigger, and so it's going to go to infinity. So we have that nice relationship. Be careful that you don't mix them up. Next one, p-series. So this one was our summations of n equals 1 to infinity of 1 over n to the p. Notice we're starting at 1, not 0, because we can't divide by 0. Now we will converge for our p being greater than 1, and we will diverge p being less than or equal to 1. Do it this way. Less than or equal to 1. And so one of the common ones here was a summation from n equaling 1 to infinity of 1 over n, which was the harmonic series. In this one, since it's a p-series where n equals 1, it will diverge. One of the other common ones was a summation of n equals 1 to infinity of 1 over n squared. And then this one would converge because our n is greater than 1. So it was using these two basic examples that always helped me remember your convergence, divergence setup. But your p-series is often something that's used when dealing with your comparison test. Now the book leaves out the alternating series test, the root test, and the limit comparison test. So you might want to review a bit on those. The divergence test was pretty easy. When you have your summation, and you have your term in the middle or inside, if the limit of that a sub n does not equal 0, then our summation will diverge. And let me leave some more room here. So our limit as n goes to infinity, if I can draw infinity, there we go, does not equal 0. Then our summation of our a sub n x minus x naught to the n power will diverge. Which makes sense that we need this part here to get really, really small in order for any of this to diverge. If it's big, we're gonna add up big numbers. But as we're adding to infinity, we need tiny little numbers added. So if this goes to something else, if it goes to a certain value, will be adding up a certain amount, an infinite number of times. So therefore, it will go to infinity. And we can move on to the next one. One we're going to use is the ratio test. And for the ratio test, they did the a sub n plus 1 divided by a sub n and did your limit. So limit as n goes to infinity of the absolute value, because that's important, of a sub n plus 1 x minus x naught n plus 1 over a sub n x minus x naught n. Now, depending on what this equals, we'll see what's going to happen. So we can do some simplification, that we know that these are going to simplify and that this thing will cancel with all of those. We're just left with this on top. And there's no n's involved in here, so we can pull that out, make sure it's still inside the absolute value though. And that should be an infinity. And we still have this a sub n plus 1 over a sub n. And then we're going to see what happens. And now if this thing is less than 1, we will converge. If this thing is greater than 1, we will diverge. But if it equals 1, we have no clue. It's inconclusive. We have to find a different test in order to use. So smaller numbers are good. Less than 1, converge. Greater than 1, diverge. Equal to 1, not so sure. But we use this ratio test a lot when dealing with our radius of convergence. And then after we find our radius of convergence, we find what's called the interval convergence. And so in this one, we're going to have our absolute value of our x minus x naught p less than p, but we want to get that entire group of numbers. So essentially, your x naught minus p up to your x naught plus p. But we don't know about these endpoints. So we would then need to check to see, is this included or not? Is this included or not? So we have to plug those back in. Now, before we do an example, let's get through the rest of these general notes. So our operations with our series. So we're first going to set up that the summation of n equals 0 to infinity of a sub n x minus x naught of n, or to the n, is going to equal some value f of x, depending on what x we put in there. And we're going to do the same thing, but we're going to do b sub n. And we'll say that equals some function g of x. And they will both converge for some rho, which is going to be our radius of convergence. So we're going to have the same one, just to make life a little bit easier with setting all this up and combining them. And we can make that a better looking G. So now let's look at our properties. So if we do f of x plus or minus g of x, that's going to be the summation of our a plus or minus the summation with our b. But if you look what we have here, it's the same summation. We have the same thing they're being multiplied by. We're doing the same indices, and it's plus or minus. So we can combine this into just an a plus or minus the b. And let me get rid of that, make that a little bit nicer with an n. So that's nice. Plus or minus, we can bring them together. What about multiplication? This can be one summation with your a's times the b's. Now, if we would add all these up and multiply them all out, our a's are going to give us a really big polynomial. The b's give us a really big polynomial. So then we can just multiply that entire thing out, and what we'll end up with is a new summation, which is a big polynomial. And so for our c sub n, it's going to be an a naught bn. Make that b look a bit nicer. Plus an a1 b n minus 1 plus, and we keep on doing this where our a values get bigger, the b values get smaller. So we get an a n minus 1 b sub 1 plus an a n b sub 0. So it's a really big, long, drawn out setup, but it is something that's doable. And we cannot just multiply the a and b. It's a whole bigger setup, bigger ordeal. So it's simple with addition, subtraction. It's a little bit more complicated with multiplication. What about division? So this can be summation of your a's over summation of your b's. And again, it will combine to give some new combination, as long as, of course, your g is not 0. But be careful with this, that our x's do not simply all cancel out. We do have to consider what's happening there with the whole summation. It is a big addition subtraction setup, and it is a giant polynomial divided by another giant polynomial. And a way to think of this working it out is if we would multiply this B part over to the other side, we get exactly what we have with multiplication, although in a different manner, that our B and D are multiplied together to give us A. So we can have that nice relationship. Next thing is if we would take a derivative of our function. That's taking the derivative of this entire summation. There should be a bracket on the end there. But now if you look what has an X in it, our A's have no X's. The only thing that has X's is this last little bit over here. So the n would come down and we have just a normal power rule derivative. So we can do derivatives inside of the summation, because if you think back to your normal derivative rules, if you are doing the derivative of a sum of a bunch of functions, it's the individual derivatives of the individual terms and then add it all together. So we can do that here as well. We can then take a second derivative, we can take a third derivative, we can take a fourth derivative, we keep on doing that. And integrals will work the exact same way. So some special cases. First one they talked about is the Taylor series. So in this case, our a sub n is given by the nth derivative at some value x naught divided by n factorial. And let's make that a better. Oh. Of course, in this case, we need our f to be infinitely differentiable. If we would happen to have a situation where our summation for our a's equals the summation for our b's, for all of our x's, then each of our n's has to equal, or each of our a's has to equal each of the b's throughout that sequence. That's for our n's equaling 0, 1, 2, and so on. That's if they're equal for every x value. Another one, if our summation equals 0, for all of our x's that are in our integral conversions, then we know that every one of our a values has to equal 0 as well. Now, it might happen the summation equals 0 for a specific x, but it happens for all the x's that we know that our a sub 0 has to equal 0, especially whenever x's are not equal to x naught. Our last big idea is what we call the shift of index. So we're going to change the values on the bottom So having an n equals 0 to infinity of some a sub n. This is going to be a sub 0 plus a sub 1 plus a sub 2 plus, and so on. We could rewrite this as using i's instead of the n's, and we still get the exact same series. But then we can do more changes to this. And things just shifted on me. There we go. That as long as whatever we have is in our equation down here still gives us the same results. So we still want this to be starting with 0 as the first term. So we change our n to 2 so that it still equals 0. So we can do adjustments on what we're starting with here if we adjust how we represent our subscript there so that we get the same results for all of our n values or indices as we are going through our sequence. So we have to make sure that we get the same sequence when we write the summation. So we need to have, in this case, a sub 0 plus a sub 1 plus a sub 2. So we can't change any of that. And we have to have the same starting point in the index to add and subtract summations. So if we would try to add, starting from n equals 1 to infinity of a sub n, with starting from n equals 2 to infinity of b sub n, we could not just do our little shortcut that we did before. So we would have to make a change. So in this case, if we want everything to start at a 1 with our subscript here, then this would have to be n plus 1, because we want the first term with our b's equal 2. So now when we plug a 1 in, we do indeed get a 2. So then we could combine these together in this form, and that would be okay. So there was the big crash course of running through the power series. Let's get one example done of finding the interval of convergence and well, first the radius of convergence, then the interval of convergence. And then that should be good enough as a reminder for you. We can go from there. So if I can move these things out of the way. Let's try this. We want the summation from n equals 1 to infinity of x to the n over n 2 to the n. So we want to use our ratio test. Limit as n goes to infinity of x to the n plus 1 over n plus 1 2 to the n plus 1. All over x to the n over n 2 to the n. letters there are running together. So let's divide things in divide fractions. Now things will simplify. These will cancel with all those, one left on top. These will cancel with all of those, one left on the bottom. And then we can factor in n out. And on the bottom, we'll have a 1 plus 1 over n. And those will cancel. This part will just go to 1, so we can pretty much ignore it. So we're left with x over 2 inside the absolute value. And this has to be less than 1 in order for it to converge. So we know that our x over 2 has to be between -1 and 1. So let's multiply by 2. So we have an overall big jump from -2 up to 2. Now the radius is from some middle point, how far do we travel in each direction? So in this situation, our rho is equal to 2. There's our radius of convergence. But now we need to figure out which values will converge for. So it's going to go up to potentially, well, down to -2 and up to 2. So we have part of our radius of or our interval convergence done. We still have to check our endpoints. So let's plug a -2 into the original. And if we do some simplification, that's supposed to be a -1. Those will cancel. And if you remember this is an alternating series, so this one will converge. So at -2, we have convergence. Let's plug a +2 in. Those cancel. Harmonic series, it diverges. So our radius of convergence is going to be 2. The interval of convergence is going to be inclusive -2 up to non-inclusive +2. And so there's a bunch more examples you can do. There's some in the book, just to walk through and remembering how to do these and all the little details. But there's your quick run through of power series, bringing back fond memories from calc. We will pick up on 5.2 in class on Monday, and then getting to using this in more of a differential equations way.